The oldest light in the universe has a pattern that should not exist, and nobody can tell you what put it there. But the story of how we found it is actually 3 separate stories that nobody has connected for you. Why did a PhD student at Imperial College London, working under a Portuguese physicist who had already been blacklisted for proposing that the speed of light used to be faster, give a feature of the cosmic microwave background, the most provocative name in the history of cosmology, and then leave academia entirely to work in finance? What does a 70 microkelvin cold spot in the constellation Eridanus have to do with a physicist who grew up behind the sealed borders of communist Albania and predicted it using the multiverse? And why, on July 9th of 2025, did the United States Department of Energy quietly cancel the only instrument on Earth that could have answered the question these anomalies have been asking since 2003? These are the same story. They point to the same direction in the sky. And by the time you understand why that direction matters, the cold spot, the axis, the cancellation, all of it will be the least disturbing part of what the data actually shows. Tonight is a long one, so settle in and get comfortable. If you are not subscribed, now is a good time. There is a Patreon where we go deeper into physics, cosmology, and the parts of the story that do not fit in a single video. Stay to the end of this one, because the direction those patterns point in is something that should have been front page news. And the reason it was not is worse than the patterns themselves. Let's start where it started. There is a direction in the sky that should not exist. Not a galaxy, not a quasar, not some object you can point a telescope at. A direction, a preferred orientation embedded in the oldest light in the universe. Light that has been traveling for 13.8 billion years, since 380,000 years after the Big Bang, since the moment the cosmos cooled enough for the first hydrogen atoms to form, and photons could finally move without slamming into free electrons every fraction of a second. That light fills the entire sky. It comes from every direction. It arrives as a faint microwave glow at a temperature of 2.725 Kelvin, just a few degrees above absolute zero, and it has been measured with a precision that makes your jaw tighten. 1 part in 100,000, 50 million pixels, 3 independent space missions spanning 3 decades of observations. And when scientists finally mapped it at that resolution, when they had more data points than they could have dreamed of, in 1965, when 2 confused radio engineers first heard it as a persistent hiss in their antenna, they found something that should not be there. Patterns, alignments, asymmetries, structures on the largest possible scales, spanning the entire observable universe. Features that every prediction from the standard model of cosmology says should not exist. And this is the part that keeps a certain group of cosmologists awake at night. Every single one of those patterns points in approximately the same direction. They converge. They cluster, as though the oldest light in existence remembered something about the geometry of the cosmos that our models say it should have forgotten. And here is where it gets worse. That direction, the direction where all the anomalies converge, is not pointing at some random patch of deep space. It is aligned to within a few tens of degrees with the plane of our solar system's orbit around the sun, with the ecliptic, with us. That should have been front page news. It was not. It was published, peer-reviewed, confirmed across 3 separate satellite missions, and then quietly filed under the heading Anomalies in companion papers that most people have never heard of. The flagship results, the ones that made the headlines, were about how perfectly the data matched the standard model. And they did match, spectacularly. The cosmic microwave background is one of the greatest triumphs of modern cosmology. But the anomalies are real. They have survived every attempt to explain them away, and the instrument that was supposed to finally settle whether they are a fluke or a crack in the foundations of everything we think we know about the universe was cancelled by the United States Department of Energy in July of 2025. I spent an unreasonable number of hours reading the actual papers on this, the Planck collaboration papers, the WMAP analyses, the independent reviews, the rebuttals, the counter-rebuttals. What I found is a story that no popular science channel has told you properly, because telling it properly requires you to sit with something genuinely uncomfortable. The possibility that the universe is not what we were told it is, not in a vague, poetic, the cosmos is full of mysteries way, in a specific, mathematically precise, published in physical review letters way, in a way that either breaks the single most important assumption in all of cosmology, or suggests something so strange about our position in the universe that most physicists would rather not say it out loud. And it starts, as these things often do, with pigeon droppings. In 1964, two radio astronomers named Arno Penzias and Robert Wilson were working at Bell Telephone Laboratories in Holmdel, New Jersey. Penzias had been born in Munich in 1933, the son of a Jewish family. He was sent to England on the Kindertransport at age 6, reunited with his parents in New York, earned his PhD in physics at Columbia in 1962. Wilson was from Houston, Texas, a quiet, methodical experimentalist who had completed his PhD at Caltech. The two of them were using a 20-foot horn reflector antenna, an imposing structure of aluminum and steel that had originally been built to detect signals bounced off the Echo Balloon satellite, and later the Telstar communications satellite. By 1964, the satellite work was done, and Penzias and Wilson had repurposed the antenna for radio astronomy, specifically for making precision measurements of radio signals from the Milky Way. They had a problem. No matter where they pointed the antenna, no matter what time of day, no matter what season, there was a persistent background hiss they could not eliminate. It corresponded to an excess antenna temperature of about 3.5 Kelvin above what their models predicted from known sources. They checked every connection, every cable, every bolt. They checked for radiation from New York City, 60 miles away. They checked for interference from nuclear weapons tests in the atmosphere. They found that a pair of pigeons had been nesting inside the horn and had coated the interior with what Penzias politely referred to in interviews as a white dielectric material. They trapped the pigeons, drove them to a release site 30 miles away. The pigeons flew back. They were eventually removed permanently, and the antenna was cleaned. The hiss remained. After months of systematic checks and rechecks, Penzias and Wilson concluded that the excess radiation was real, isotropic, unpolarized, and unexplained. 40 miles away, at Princeton University, a physicist named Robert Dicke had independently predicted that such a radiation field should exist, the cooled remnant of the hot, early universe. And his group was building a radiometer to detect it. When Penzias called Dicke to discuss the excess signal, Dicke reportedly turned to his colleagues and said, "Boys, we've been scooped." The Princeton group published the theoretical interpretation. Penzias and Wilson published the detection. Their paper appeared in the Astrophysical Journal in 1965, volume 142, with the exquisitely understated title, "A Measurement of Excess Antenna Temperature at 4080 mc per s." It is 3.5 pages long. It describes the antenna, the calibration, the systematic checks, and the result. It does not mention the Big Bang. It does not mention cosmology. It simply reports a measurement. And that measurement changed everything. Penzias and Wilson shared the 1978 Nobel Prize in Physics. Dick, who had predicted the radiation and whose theoretical work made the discovery meaningful, did not share it. Neither did Jim Peebles, who had been the graduate student in Dick's group doing the actual calculations, and who had to wait until 2019, at the age of 84, to receive his own Nobel for other contributions to cosmology. That particular injustice is its own story, but it sets a pattern you will see repeated throughout the history of the CMB. The people who take the biggest intellectual risks are not always the ones who receive the recognition. The people who have the idea do not always get the prize. And the institutions that award prizes have their own narratives, their own preferences, their own blind spots. The CMB became the cornerstone of modern cosmology, the single most important piece of evidence that the Big Bang actually happened. And it is worth pausing to understand what the CMB actually is, physically, because the physics is what makes the anomalies so unsettling. The universe began hot, unimaginably hot. In the first seconds after the Big Bang, the temperature was billions of degrees, too hot for atoms to exist. Protons and electrons flew freely in a dense plasma, and photons, light, bounced between the charged particles constantly, unable to travel more than a tiny distance before being scattered. The mean free path of a photon in this plasma was shorter than a centimeter. The universe was opaque, not dark. It was blazingly bright, but opaque in the sense that no light could travel in a straight line. If you had been there, you would have seen nothing, just a featureless glowing fog in every direction. As the universe expanded, it cooled, and roughly 380,000 years after the Big Bang, the temperature dropped through about 3,000 Kelvin, and something irreversible happened. The electrons slowed down enough to be captured by protons. Neutral hydrogen formed, and neutral hydrogen does not scatter photons the way free electrons do. The fog cleared. In cosmology, this event is called recombination, a misleading name because the electrons and protons had never been combined before. But the name has stuck for decades, and nobody is going to change it now. At the moment of recombination, every photon in the universe was suddenly free to travel in a straight line, forever. Those photons have been traveling ever since, stretching with the expansion of space, their wavelengths growing longer, their energy diminishing, until what was once a blindingly bright 3,000-degree glow has cooled to a faint microwave whisper at 2.725 Kelvin. That whisper is the CMB. It fills the entire sky. It comes from every direction, and every pixel of it carries information about the physical conditions at that location on the surface of last scattering. The spherical shell, 13.8 billion light-years away, where the universe became transparent. When you look at the CMB, you are not looking at a distant object. You are looking at a moment in time, the boundary of the visible cosmos. Everything inside that shell is the universe we can observe. Everything outside it is hidden behind a wall of plasma. The CMB is the wall. It is the first and last photograph the universe ever took of itself. But the discovery itself was not the important part, not in the long run. The important part was what came next, the question that would consume 3 generations of physicists and $3 billion worth of satellite missions. The CMB should be perfectly smooth. If the Big Bang was uniform, if the initial conditions of the universe were the same everywhere, if space expanded the same way in every direction, then the afterglow should have exactly the same temperature, no matter where you look. 2.725 Kelvin in every direction. Featureless, isotropic, the most boring map imaginable. I need you to understand what isotropic means in this context, because it is the most important word in this entire script. Isotropic does not just mean looks the same everywhere. It means there is no preferred direction, no axis, no orientation, no distinction between up and down or left and right. If you rotated the entire universe by any angle around any axis, the statistical properties of the CMB would be unchanged. Not the individual hotspots and cold spots. Those are random. But the overall statistics, the average power at each angular scale, the probability distributions, the correlations, all of those should be identical regardless of which direction you look. This is not a small assumption. This is the cosmological principle. It is the foundational axiom upon which the entire standard model of cosmology is built. Every Friedmann equation, every dark energy calculation, every measurement of the Hubble constant, every estimate of the age of the universe, all of it rests on this assumption. If the universe has a preferred direction on the largest scales, then the equations that govern its expansion may need direction-dependent terms. The Friedmann equations, which describe how the scale factor of the universe evolves over time, assume perfect homogeneity and isotropy. If isotropy is violated, those equations are an approximation, not a description. And nobody knows how good that approximation is. The mathematical language makes this concrete. You can decompose the CMB temperature map into spherical harmonics, which are the natural mathematical functions on the surface of a sphere. Think of them as the equivalent of Fourier modes for a curved surface. Each harmonic is labeled by two numbers, the multipole L and the order M. The multipole tells you the angular scale. Low L means large angles, features that span the sky. High L means small angles, features the size of a fraction of a degree. The coefficients of these harmonics, called the A sub LMs, encode all the information in the map. Under the standard model, these coefficients should be independent, complex Gaussian random variables. Their variance, called C sub L, should depend only on L, not on M. And the C sub L values are the power spectrum, the single most important data product in CMB cosmology. When the WMAP power spectrum was published, it matched the lambda CDM prediction with a precision that made cosmologists weep with joy. 6 numbers, 6 parameters that describe the entire universe: the density of baryons, the density of dark matter, the age of the universe, the optical depth to reionization, the amplitude of primordial fluctuations, and the spectral tilt. Adjust those 6 knobs, and the theoretical power spectrum slides into perfect alignment with the observed one across thousands of multipoles. It was the greatest fit in the history of physics. Nothing in any field of science has ever matched a prediction that precisely over that many orders of magnitude. But the power spectrum is a summary statistic. It tells you how much power exists at each angular scale. It does not tell you where that power is located on the sky. It does not tell you whether the power is distributed isotropically. It does not tell you whether the quadrupole is aligned with the octupole. It is blind to direction. And when you look beyond the power spectrum, when you look at the full information contained in the A sub LM coefficients and ask whether they really are isotropic, really are Gaussian, really are independent, the picture changes. But the universe is not featureless. Galaxies exist. Galaxy clusters exist. The large-scale structure of the cosmos, the cosmic web of filaments and voids, exists. And all of that structure had to grow from something. Tiny density fluctuations in the early universe, places where there was slightly more matter than average, and places where there was slightly less. And those tiny fluctuations were amplified by gravity over billions of years into the structures we see today. If the fluctuations existed, they should be imprinted on the CMB as tiny temperature variations, hot spots and cold spots, at the level of about 1 part in 100,000. That is 18 millionths of a degree. The difference between a hot spot and a cold spot in the CMB is roughly 100 times smaller than the width of a human hair compared to a football field. Finding those fluctuations became the holy grail of observational cosmology. It took nearly 3 decades. On November 18, 1989, NASA launched the Cosmic Background Explorer, COBE, from Vandenberg Air Force Base in California. It had originally been designed to fly on the Space Shuttle, but after the Challenger disaster in 1986, the mission was redesigned for a Delta rocket and launched 3 years behind schedule. COBE carried 2 instruments that mattered. FIRAS, the Far Infrared Absolute Spectrophotometer, led by John Mather, measured the spectrum of the CMB with extraordinary precision and found it was a perfect blackbody curve, matching the theoretical prediction to better than 50 parts per million. When Mather presented the spectrum at an American Astronomical Society meeting in January of 1990, the audience gave it a standing ovation. It was that clean, a perfect curve, no deviations. The CMB was exactly the thermal radiation you would expect from a hot, dense, expanding universe that had been cooling for 13.8 billion years. But it was the other instrument, the differential microwave radiometer, DMR, led by George Smoot at the University of California, Berkeley, that changed everything. DMR mapped the temperature of the CMB across the sky at a resolution of about 7 degrees and found the fluctuations. Tiny ripples in the temperature at the level of about 30 millionths of a degree, roughly 1 part in 100,000. On April 23, 1992, Smoot announced the results at an American Physical Society meeting in Washington. The press conference was by most accounts a spectacle. Smoot reportedly said something along the lines of, "If you are religious, this is like looking at the face of God." The press shortened it, and it made every front page in the world. Stephen Hawking called it the discovery of the century, if not of all time. There is a detail in that press conference that matters for what comes later. Smoot held it largely on his own. COBE was a team effort involving over 1,000 scientists and engineers, coordinated across multiple NASA centers. John Mather and many others were reportedly unhappy about the way Smoot positioned himself as the singular face of the discovery. The tension between the individual hero narrative and the collaborative reality of big science is something you need to keep in mind, because it matters when we get to how the anomalies were handled. Big collaborations have institutional interests, they have press offices, they have stakeholders, they have a narrative to maintain, and institutional interests do not always align with uncomfortable discoveries. 14 years later, in 2006, Mather and Smoot shared the Nobel Prize in Physics for COBE, with the citation reading, "For their discovery of the blackbody form and anisotropy of the cosmic microwave background radiation." The Nobel Committee chose to award 2 individuals for a project that involved over 1,000 people. The Nobel Committee chose 2 people who had a complicated relationship with each other. And the story they told was about triumph, about confirmation, about how the CMB proved the Big Bang and opened the door to precision cosmology. That is a true story, but it is not the complete story. COBE found the ripples, but its resolution was crude. 7 degrees is enormous, roughly 14 times the apparent size of the full moon. Imagine trying to read a newspaper by looking at it through frosted glass. You can see that there is text that the page is not blank, but you cannot make out the letters. COBE told us the CMB had structure. It could not tell us the details of that structure. And the details matter, because the precise pattern of hot and cold spots at different angular scales encodes an extraordinary amount of information about the physics of the early universe. The relative heights of the peaks in the power spectrum tell you the ratio of ordinary matter to dark matter. The angular position of the first peak tells you the geometry of space, whether it is flat, positively curved, or negatively curved. The damping of the peaks at small scales tells you when the first stars formed and reionized the universe. Every feature in the power spectrum is a measurement, but you need resolution to see those features. Between COBE and WMAP, a generation of ground-based and balloon-borne experiments pushed the resolution frontier. Boomerang, a balloon experiment launched from McMurdo Station in Antarctica in December of 1998, mapped a patch of sky at a resolution of about 12 arc-minutes and provided the first strong evidence that the geometry of space is flat. Maxima, another balloon experiment, confirmed the result. Darcy, the degree angular scale interferometer at the South Pole, detected CMB polarization for the first time in 2002. These experiments were brilliant, heroic in their engineering, and fundamentally limited. They could map only small patches of sky. To see the full picture, to measure the power spectrum across all angular scales with the precision needed to nail down the cosmological parameters, you needed a satellite. You needed to get above the atmosphere. You needed to see the whole sky. That something arrived on June 30th, 2001, when NASA launched the Wilkinson Microwave Anisotropy Probe, WMAP, from Cape Canaveral. WMAP was named after David Wilkinson, a Princeton physicist who had been part of Dick's original group in 1965 and who had died in September of 2002 before the first results were released. It was a fitting tribute. Wilkinson had spent his career building instruments to study the CMB, from the first Princeton radiometer that was scooped by Penzias and Wilson, all the way through COBE and the early planning stages of WMAP. He never saw the results that his life's work made possible. WMAP mapped the CMB at a resolution of about 13 arc-minutes, roughly 100 times sharper than COBE, using 5 frequency bands to separate the cosmological signal from galactic foregrounds. The satellite orbited the second Lagrange point, L2, 1.5 million kilometers from Earth, where thermal stability was excellent, and the Sun, Earth, and Moon were always behind its sunshield. The team was led by Charles Bennett at Johns Hopkins and David Spergel at Princeton, and when the first-year data was released in February of 2003, it was a triumph. Not a modest success, not a confirmation with caveats, a triumph. The power spectrum matched the predictions of the lambda-cold dark matter model with a precision that silenced skeptics. The age of the universe was measured to 13.7 billion years, later refined by Planck to 13.8. The geometry of space was measured to be flat to within 1%. The composition of the universe was nailed down to quantities that sounded like they belonged in a recipe. Roughly 5% ordinary matter, 27% dark matter, 68% dark energy. Cosmology had entered its precision era, and the CMB was the jewel in the crown. Spergel and Bennett and the WMAP team won prizes and accolades. The 2003 first-year paper became one of the most cited papers in the history of physics, and the narrative that emerged was simple, satisfying, and complete. We understand the universe. The standard model works. The CMB confirms it. Case closed. But there was a problem. The WMAP data was so precise that for the first time you could run tests that had never been possible before. tests of the foundational assumption, tests of isotropy, tests to see whether the CMB really did look the same in every direction at every angular scale, the way every model said it should. The tests had always been there in principle, but COBE did not have the resolution. And before COBE, the CMB was not even a map, just a temperature and a spectrum. WMAP was the first time you could actually take the cosmological principle and check it against data point by data point across the entire sky. When the WMAP team ran those tests on their first-year data, the results were unsettling. The largest angular scales, the quadrupole and octopole, the patterns that span the entire sky, were not behaving the way they should. They were aligned, not randomly oriented the way every model predicted, but lined up along a common axis, and the amount of power at those largest scales was lower than expected, significantly lower. I need to explain why this matters, because the mathematics here is not decorative, it is load-bearing. The two-point correlation function, written as C of theta, measures something specific. You pick a point on the CMB sky, you measure its temperature, then you pick another point, some angular distance theta away. You measure its temperature. You multiply those two temperatures together. Then you repeat this for every possible pair of points separated by that angle and average the results. Do this for every possible angle from 0 to 180 degrees and you get the two-point correlation function. It tells you how much the temperature at one point on the sky knows about the temperature at another point far away. Under lambda CDM, the two-point correlation function has a specific predicted shape. At small separations, it should be positive because nearby points tend to have similar temperatures. At intermediate separations, it oscillates through 0 and goes negative. At very large separations, above about 60 degrees, it should settle into a pattern that reflects the low multipole power, the broad, sky-spanning patterns imprinted by physics at the largest scales during inflation. The prediction is specific and non-negotiable. If lambda CDM is correct, C of theta at large angles should have a particular value and a particular shape. What WMAP found was that above 60 degrees of separation, C of theta was consistent with 0, not slightly below the prediction, not somewhat reduced, but consistent with 0. The temperature at one point on the sky showed essentially no correlation whatsoever with the temperature at a point 60 degrees or more away. It was as if someone had taken the large-scale patterns, the ones that span the entire sky, the ones that are supposed to be the cleanest, most direct imprint of inflation, and erased them. The probability of this happening by chance under standard lambda CDM was less than 1 in 1,000. In the cleanest frequency channel, less than 1 in 3,000. And here is the part that should bother you about how this was handled. The WMAP team reported this result. It was in their papers. It was in their data products. Anyone could download the maps and verify it. But the first-year WMAP release was dominated by the spectacular success of the power spectrum fit. The press conference was about how lambda CDM works. The anomaly was noted. It was not emphasized. The team chose to lead with triumph and file the discomfort in the supplementary material. That was 2003. The anomalies had arrived, and the fight over what they mean has been going on ever since. I need to be precise about what I mean by anomalies, because the word gets thrown around loosely, and precision is the only currency that matters here. There are 4 major anomalies. They were found in WMAP data between 2003 and 2005. They were confirmed in Planck data in 2013, and again in 2018. They have survived every systematic check, every change of instrument, every change of analysis pipeline, every change of foreground removal method, They are real features in the data. What is contested is not whether they exist, but whether they are statistically significant, which is a very different question and one that reveals more about the sociology of science than about the physics. The first anomaly is the one I already mentioned, the lack of large angle correlations. Above roughly 60 degrees of angular separation, the CMB temperature fluctuations simply do not correlate with each other the way lambda CDM says they should. This was quantified most precisely by a group of 4 physicists who have been publishing papers on this since 2004 and who have become, in my mind, the conscience of the field. Craig COBE at Case Western Reserve University in Cleveland, Drugan Huterer at the University of Michigan, Dominique Schwartz at Bielefeld University in Germany, Glenn Starkman at Case Western. These 4 have been systematically, methodically, year after year, documenting the anomalies and pointing out that they lack a convincing explanation. And the response of the broader community has been a kind of polite acknowledgement that never quite rises to engagement. Their 2015 paper, published in Monthly Notices of the Royal Astronomical Society, Volume 451, is the definitive statement. They calculated p-values for the missing correlations and found them lying below 0.24%, which is evidence at more than 3 sigma for foreground cleaned maps. And their conservative analysis of the Planck HFI 100 GHz frequency band, the cleanest CMB channel, returned a p-value as small as 0.03%. That is 1 chance in roughly 3,000. Their conclusion is as direct as academic prose permits. These findings are in stark contrast to expectations from the inflationary lambda cold dark matter model, and still lack a convincing explanation. That phrase, still lack a convincing explanation, it has appeared in their papers for over a decade now, each time with updated data, each time with the same conclusion. And each time, the broader cosmological community nods politely and moves on. But the second anomaly makes the first one worse. In 2004, a physicist named Patricio Vielva at the Instituto de Física de Cantabria in Santander, Spain, published a paper in the Astrophysical Journal, volume 609. Vielva was barely a year past his PhD, which he had completed at the University of Cantabria in 2003. He was young, part of a strong observational cosmology group at IFCA, led by Enrique Martinez Gonzalez, and he was working on wavelet techniques for analyzing CMB maps. The method his group used was called the spherical Mexican hat wavelet transform. If you have never heard of a wavelet transform, think of it as a way to look at a map through a series of differently sized magnifying glasses. Each wavelet scale highlights features of a particular angular size while suppressing everything else. You tune the magnifying glass to 4 degrees and you see features of about 4 degrees. You tune it to 10 degrees and you see 10-degree features. It is an effective way to find localized anomalies that might be invisible in the global statistics. When Vielva's team looked at the WMAP first-year map through a wavelet tuned to angular scales of about 4 to 5 degrees, they found something that should not have been there. A cold spot, a region of sky in the southern hemisphere, in the direction of the constellation Eridanus, at galactic coordinates of approximately 209 degrees longitude and minus 57 degrees latitude. The temperature of the CMB in this region was anomalously low, about minus 70 microkelvin relative to the average, with the deepest points reaching down to minus 140 or 150 microkelvin depending on how you define the aperture. The spot subtended about 5 degrees on the sky, roughly 10 times the apparent diameter of the full moon. And when the team ran Monte Carlo simulations, generating 10,000 random Gaussian skies and running the same wavelet analysis on each one, Fewer than 2 in 1,000 produced a feature that extreme. Pedro Cruz and colleagues at the same institute followed up in 2005 in monthly notices of the Royal Astronomical Society, volume 356, localizing the spot more precisely and computing the probability at about 0.2%, roughly 3 sigma. Think about what that means. You take the standard model of cosmology, the model that says the CMB should be a random Gaussian field with no preferred locations. You generate 10,000 fake skies from that model, and in fewer than 20 of them do you find anything as cold as what is actually sitting there in Eridanus. Not definitive, but deeply uncomfortable, especially because the cold spot is not just statistically anomalous, it is visually obvious. When you look at the Planck map of the southern sky with the color scale set to highlight temperature variations, there it is, a dark blue disk, a hole in the oldest light in the universe. The cold spot became famous almost immediately, and the natural instinct of the cosmological community was to find a normal explanation, something that did not require new physics, something that could be understood within the framework that had worked so spectacularly well at smaller angular scales. In 2015, a team led by Istvan Sapudi at the Institute for Astronomy at the University of Hawaii published a paper in Monthly Notices, volume 450, reporting the detection of a supervoid aligned with the cold spot. Sapudi is Hungarian-American, born in Budapest, earned his master's in theoretical physics at Eötvös University in 1990, his PhD in astrophysics at Johns Hopkins in 1995 under Alex Saleh, and had been at the University of Hawaii since 2001. He used data from the WISE and 2-mass galaxy surveys, cross-matched with pan-stars photometry to map the three-dimensional distribution of matter in the direction of the cold spot. What he found was an enormous underdensity, a void with a radius of roughly 220 megaparsecs, centered at a redshift of about 0.22, with a central density contrast of about minus 0.14. Popular press reports described it as 1.8 billion light-years across, one of the largest known structures in the universe. The idea was straightforward and elegant. When a CMB photon travels through a large void, it enters the void, gains energy climbing out of the gravitational well on the near side, crosses the void, and then loses energy climbing into the gravitational well on the far side. If the void is not expanding, those two effects cancel perfectly. But the void is embedded in an expanding universe with dark energy, and during the time the photon crosses the void becomes emptier. The gravitational well on the far side is shallower than the one on the near side. The photon loses more energy leaving than it gained entering. This is called the integrated Sachs-Wolf effect. A sufficiently large void at the right distance could, in principle, create a measurable cold spot in the CMB. Problem solved. The cold spot is just the shadow of a giant void. Nothing exotic required. But the numbers did not work. In 2017, Thomas Mackenzie and a team including Tom Shanks at Durham University published a paper in Monthly Notices, volume 470, titled Evidence Against a Supervoid Causing the CMB Cold Spot. They used the 2-degree field VST Atlas Cold Spot Redshift Survey to measure actual galaxy redshifts in the cold spot region, not photometric estimates, but spectroscopic measurements, and calculated the integrated Sachs-Wolf effect of the voids they found. The result was minus 9.1, plus or minus 6.1 microkelvin. The cold spot is minus 70 microkelvin. The supervoid explains roughly 10 to 20% of the signal. Their conclusion was as direct as published cosmology gets. the CMB cold spot could not have been imprinted by a void confined to the inner core of the cold spot. The cold spot may have a primordial origin rather than being due to line-of-sight effects. The supervoid is real. The supervoid is there, but it is not the answer, not even close. And the gap between explanation and reality is enormous. Imagine you have a wound that is 70 units deep, and someone offers you a bandage that covers 9. That is the relationship between the cold spot and the supervoid. The explanation does not merely fall short. It fails by a factor of 4 to 7, depending on how you run the numbers. And the fact that the supervoid explanation was presented in 2015, as if it were the answer, that headlines ran saying, "Mystery solved," and astronomers find large hole in universe that explains CMB cold spot, and that the actual quantitative analysis showing it explains less than a fifth of the signal, came out 2 years later to much less fanfare, tells you something about how the field handles uncomfortable results. The comfortable explanation is amplified. The inconvenient follow-up is published and noted and then quietly set aside. The public walks away thinking the cold spot was explained. It was not. It remains, as of today, one of the most anomalous features in the most precisely measured dataset in the history of science. And this is where the story gets stranger, because a physicist named Laura Mersini-Houghton had predicted the cold spot years before its full observational significance was widely accepted. And her prediction did not come from lambda CDM cosmology. It came from the multiverse. Mersini-Houghton's biography is one of those stories that sounds like it should be a film. She was born in Tirana, Albania, during the Hoxha era, one of the most isolated and repressive communist regimes in 20th century Europe. Her father, Nekshat Mersini, was a mathematician and economist. She grew up in a country where travel was forbidden, where information was controlled, where the borders were sealed. She earned her undergraduate degree at the University of Tirana, and in 1994, after the fall of communism, she came to the United States as a Fulbright scholar at the University of Maryland College Park. She completed her PhD at the University of Wisconsin-Milwaukee and joined the faculty at the University of North Carolina at Chapel Hill in January of 2004. The same year, Vielva published The Cold Spot Discovery. She was tenured in 2008. In a series of papers published between 2006 and 2008, most notably Cosmological Avatars of the Landscape, Parts 1 and 2. The latter posted on Arxiv as HEP DO612-142. She proposed something that sounded, at the time, like theoretical extravagance. If the string theory landscape is real, if our universe is one of an enormous number of possible universes that nucleated from a quantum landscape of vacuum states, then neighboring universes should have interacted with ours at the earliest moments of existence. Those interactions would leave signatures, bruises on the cosmic microwave background, giant voids, anomalous cold spots, a suppression of power at the largest angular scales. She made 5 specific, testable predictions. I want to be careful here, because this is exactly the kind of claim that can slide into speculation if you are not precise about what was actually predicted and what was actually found. Several of Mersini-Houghton's predictions align with what Planck later observed. The cold spot and the associated giant void are the most frequently cited. Her 2022 book, Before the Big Bang, The Origin of Our Universe from the Multiverse, published by Harper, makes the case directly, arguing that the cold spot is the unmistakable imprint of another universe beyond the edge of our own. She has appeared on BBC Horizon, the Discovery Channel, and the Science Channel's Through the Wormhole with Morgan Freeman. Many mainstream cosmologists consider her predictions to be retrofitted, imposed after the fact onto data that could be explained more conservatively. That is a legitimate criticism. The papers exist, the rebuttals exist, and the debate is ongoing. I am not going to tell you she is right, but I am also not going to tell you she is wrong, because nobody has proven either position. What I will tell you is this: the supervoid does not explain the cold spot. The standard model does not predict the cold spot. Something put a 5-degree, 70 microkelvin hole in the oldest light in the universe, and nobody knows what it is. Whether Mersini-Houghton's answer is correct is an open question. That there is a question at all is not. And something about her trajectory haunts me. A woman who grew up behind one of the most impenetrable borders in the world, in a country that literally sealed its citizens inside, became a physicist who studies whether our entire universe has a border and whether something pressed against it from the other side and left a mark. I am not drawing a causal connection. I am noting the poetry and the fact that the physics community treated her ideas with the particular kind of polite, distant skepticism it reserves for proposals that are too large to engage with honestly and too well constructed to dismiss outright. But the cold spot, disturbing as it is not the most unsettling of the anomalies. It is not even close, because in 2005, a paper appeared in Physical Review Letters, volume 95, that gave the most provocative name in the history of cosmology to a problem that has only gotten worse in the 2 decades since. The paper was called The Axis of Evil. The lead author was Kate Land. She was a PhD student at Imperial College London, born and raised in Sussex, an undergraduate at Cambridge, working under the supervision of Joao Magueijo. And Magueijo is one of those figures who seems almost engineered to be a character in a story like this. Born in 1967 in Évora, Portugal, physics degree at the University of Lisbon, PhD at Cambridge, Fellow of St. John's College, positions at Princeton and Cambridge, currently Professor of Theoretical Physics at Imperial College London. He had made his name in 1998 by co-proposing with Andreas Albrecht the varying speed of light theory, VSL, a radical alternative to cosmic inflation, suggesting the speed of light was enormously higher in the very early universe. The physics establishment did not embrace this. The establishment, in fact, was actively hostile. Magueijo did not take the rejection quietly. His 2003 book, Faster Than the Speed of Light, is an unsparing, at times incendiary account of academic hostility toward heterodox ideas. Publishers Weekly described him as appearing immature and almost bratty in his diatribes against the banalities of academia or the hypocrisy and backbiting of peer review. He wrote about being told his work was not physics, about having papers rejected not because the mathematics was wrong, but because the conclusion was unpalatable. In 2014, he published a book in Portuguese called Bifes Mal Passados, in which he described British culture in terms that generated headlines in The Guardian and The Telegraph. He is by any measure not a man who avoids controversy. He is a man who runs toward it. So when Magueijo and his PhD student Kate Land found something deeply wrong in the WMAP data, something that challenged the cosmological principle itself, they did not give it a measured, cautious, hedging title. They called it The Axis of Evil. The name was a deliberate pun on George W. Bush's 2002 State of the Union address, in which Bush had labeled Iran, Iraq, and North Korea the axis of evil. It was provocative, irreverent, and it stuck. To this day, 2 decades later, even the most formal Planck collaboration papers refer to the quadrupole-octopole alignment as the axis of evil. Magueijo and Land made it impossible to ignore. That was the point. Here is what they found. The CMB temperature fluctuations can be decomposed into spherical harmonics, mathematical functions on the surface of a sphere, exactly like the way a sound wave can be decomposed into its component frequencies. Each harmonic is labeled by a number called the multipole, usually written as L. Low multipoles correspond to the largest angular scales on the sky. The quadrupole, L equals 2, describes the pattern that repeats twice as you go around the sphere. The octupole, L equals 3, repeats 3 times. In a statistically isotropic universe, the orientations of these multipole patterns should be random. The quadrupole should point in one direction, the octupole in another, with no particular relationship between them. They do not. Land and Magueijo found that the quadrupole and octupole are aligned along a common axis, and not just them. The multipole vectors for L equals 4 and L equals 5 also cluster near the same direction, pointing roughly toward galactic coordinates of about 260 degrees longitude and 60 degrees latitude, which places the axis close to the constellation Virgo and perpendicular to the plane of our solar system's orbit around the Sun. When they ran 5,000 Monte Carlo simulations of Gaussian isotropic skies, generating 5,000 fake universes, and checking the alignment in each one, fewer than 5 out of those 5,000 reproduced the observed degree of alignment. That is a probability of less than 0.1%. Less than 1 in 1,000. Think about what this means. The largest patterns in the cosmic microwave background, patterns that span the entire observable universe, patterns imprinted 13.8 billion years ago when the first atoms formed, are lined up. They share an axis, and that axis has a specific direction in space. In their 2007 follow-up paper, published in Monthly Notices of the Royal Astronomical Society, Volume 378, Land and Magueijo revisited the result with 3 years of accumulated WMAP data, and found that the statistical significance was somewhat sensitive to the choice of galactic mask, the region around the Milky Way that you have to cut out of the map because our galaxy's own emission contaminates it. Using a Bayesian model selection approach, they obtained significance levels of 94 to 98% rather than the original 99.9. Still suggestive. Not as dramatic, the kind of result that gives the establishment just enough room to shrug and say, interesting, but probably noise. The Planck collaboration tested it too. Planck 2013 paper 23 confirmed the quadrupole-octupole alignment, but at a reduced significance of roughly 2 to 3 sigma. The axis sits at approximately the same galactic coordinates. The alignment is there. It has been there in COBE, WMAP, and Planck. 3 completely independent instruments, 3 different orbits, 3 different analysis pipelines, and it has not moved. And here is the biographical irony that I keep thinking about. Kate Land, the woman who co-discovered one of the most provocative findings in 21st century cosmology, the woman who co-named the axis of evil, left academic physics after her postdoc at Oxford. In a 2009 interview on the Galaxy Zoo blog, she explained her decision with a candor that is both admirable and quietly devastating. She said she personally was not keen on the postdoc circuit of moving about every few years, that she wanted to plan for the future and nest build somewhat. She thought this was more of a female thing, to agonize over the future. She moved to London and became a quantitative analyst in the financial sector. She is now a lead data scientist at a firm called Inalytics. She remains active in astronomy outreach as deputy chair of the Luz Astronomical Society giving talks about the night sky to local enthusiasts. The woman who named the axis of evil traded cosmology for the city. And the axis she found is still there, still unexplained, still pointing in a direction that nobody can account for. Magueijo stayed in physics. He is still at Imperial College, but the academic establishment never quite embraced either the axis of evil or his varying speed of light work. The pattern is familiar. First it was impossible, then when someone found it, it was probably noise. The one thing it could never be was important. But the axis was not alone. And this is where the story turns from unsettling to something that made me sit back from my screen when I first understood the full picture. Because while Land and Magueijo were arguing about galactic masks and Bayesian significance, other teams were finding other anomalies in the same data, different statistical tests, different angular scales, different research groups at different universities in different countries. And every single anomaly was pointing in the same direction. The hemispherical power asymmetry was first reported by Hans Christian Eriksson and Frode Hansen at the University of Oslo in 2004, using the same WMAP first-year data. What they found was this: divide the sky into two hemispheres along a specific axis. One hemisphere, centered roughly on galactic longitude, 226 degrees, and latitude minus 17 degrees, has about 7% more CMB fluctuation power than the other hemisphere. 7%. That does not sound like much until you calculate the probability of it happening by chance in an isotropic universe. It is about 3 sigma, one chance in roughly 1,000. You need to understand what fluctuation power means here. The CMB is not just hot spots and cold spots scattered randomly. The size and intensity of those fluctuations carry information about the physics of the early universe. The power at a given angular scale tells you about the density fluctuations at that scale in the primordial plasma. If the universe is truly isotropic, the average power should be the same in every direction. 7% more power in one hemisphere means the fluctuations are systematically stronger on one side of the sky, as though the universe had a gradient, a tilt, a direction. The asymmetry was modeled mathematically as a dipole modulation of the temperature field, with an amplitude of about 7% at a confidence level of around 3 sigma. And it was confirmed by Planck. The 2023 reanalysis using the latest Planck PR4 data release by Alluri and colleagues found the asymmetry persisting at approximately 3 sigma in temperature data. Even in E-mode polarization it shows up, though at a somewhat reduced amplitude of about 2.8%. Their November 2024 reassessment concluded, in language that is politely but unmistakably frustrated, that the hemispherical power asymmetry still remains as a challenge to the standard model. In 2010, the parity anomaly appeared. Jae-Sung Kim and Pavel Naselsky at the Niels Bohr Institute in Copenhagen published a paper in the Astrophysical Journal Letters, volume 714, titled Anomalous Parity Asymmetry of the WMAP Power Spectrum Data at Low Multipoles. They decomposed the CMB into odd parity and even parity multipoles, a mathematical operation based on whether L is odd or even, and found that odd multipoles in the range from L equals 2 to L equals 18 carry significantly more power than even multipoles. The probability of this odd parity preference under lambda CDM was about 4 in 1,000, 3 sigma again. And in a crucial follow-up paper in 2011, published in the Astrophysical Journal, volume 739, Kim and Naselsky showed something that transformed the entire picture. The odd parity preference is not a separate anomaly. It is the mechanism behind the lack of large angle correlations. The large-scale temperature correlations are suppressed because the even multipoles are suppressed. The two anomalies are one anomaly wearing two masks, and the parity asymmetry has a preferred axis, and that axis aligns with the CMB kinematic dipole, which is the direction of our solar system's motion through the CMB rest frame, and with the quadrupole-octopole alignment. I need to stop and explain the kinematic dipole, because it matters enormously. The Earth is moving. The Sun is orbiting the center of the Milky Way. The Milky Way is falling toward the Virgo cluster. Our entire local group of galaxies is moving through space at roughly 369 kilometers per second relative to the cosmic microwave background. That motion creates a Doppler shift. The CMB appears slightly hotter by about 3.4 millikelvin in the direction we are moving toward, and slightly cooler in the direction we are moving away from. This dipole was one of the first features measured in the CMB, and it is well understood. It is not anomalous. It is just our local motion. The kinematic dipole points toward galactic coordinates of roughly 264 degrees longitude, 48 degrees latitude. Keep that number in your head. Now here is the convergence that nobody can explain. The axis of evil, the quadrupole-octopole alignment, points to approximately 260 degrees longitude, 60 degrees latitude. The hemispherical asymmetry axis points to approximately 226 degrees longitude, minus 17 degrees latitude. The parity asymmetry axis is in a similar region. The cold spot sits at 209 degrees longitude, minus 57 degrees latitude. All of these axes cluster within about 10 to 30 degrees of each other, and they all cluster near the ecliptic plane and near the kinematic dipole direction. Frode Hansen and colleagues published a key analysis of this convergence in 2009, extending the hemispherical asymmetry measurement from the original multipole range of L equals 2 to 40, all the way out to L equals 2 to 600, using WMAP 5-year data. This extension was crucial. It was not an after-the-fact look at the same data, hoping to find something. It was a prediction. If the hemispherical asymmetry is a real physical effect rather than a large-scale statistical fluctuation, it should extend to smaller angular scales. Hansen tested this, and it did extend. The asymmetry axis lies close to the ecliptic axis across a wide range of multipoles. I want to make sure the weight of what I have just told you lands properly. There are 4 major anomalies in the cosmic microwave background. Each one is individually a 2 to 3 sigma result. Each one individually could be waved away as a statistical fluctuation, but they all point in approximately the same direction. Their axes converge within a few tens of degrees, and that convergence direction is aligned with the ecliptic plane, the plane defined by our solar system's orbit around the Sun, and with the kinematic dipole, the direction of our motion through the CMB. Here is a common misconception that I need to correct, because it affects how you evaluate everything I have told you. Many people hear 2 to 3 sigma and think, not significant. That framing comes from particle physics, where the 5 sigma standard has become the gold standard for discovery. The Higgs boson was announced at 5 sigma. Gravitational waves were announced at 5.1 sigma. Anything below 3 sigma is considered noise. This standard makes sense in particle physics because particle physics experiments are repeatable. You can build a bigger collider. You can run more proton-proton collisions. You can accumulate more events. Every year of data brings you closer to 5 sigma or further from it. The statistical machinery is designed for repeated trials. Cosmology does not work that way. You have one sky. You have one CMB. You have one universe. You cannot rerun the Big Bang with different initial conditions and check whether the anomalies appear in the other versions. There is no bigger collider for the CMB. There is only the universe we have, and the universe has a fundamental limitation called cosmic variance, which means that at the largest angular scales, the multipoles with the lowest L values, you are measuring a single realization of a random process with very few independent samples. The quadrupole, L equals 2, has only 5 independent components. The octupole has 7. You cannot beat down the noise by collecting more data, because there is no more data to collect. The CMB has already been measured to within a fraction of its cosmic variance limit at the largest scales. No future instrument, no matter how sensitive, will significantly reduce the uncertainties on the low multipoles in temperature. The uncertainty is not instrumental, it is fundamental. So what does 3 sigma mean in this context? It means that if lambda CDM is the correct model, the probability of seeing what we see is about 1 in 1,000. That is not the same as saying the probability of lambda CDM being wrong is 1 in 1,000. The relationship between those two statements depends on prior probabilities and on the space of alternative models. And that relationship is the subject of a debate that has consumed hundreds of pages of academic literature and shows no sign of resolution. But the convergence of multiple anomalies changes the calculation entirely. This is the point that I think gets lost in most popular accounts. Any single 3 sigma result has a 1 in 1,000 chance of being a fluke. But 4 3 sigma results, all pointing in the same direction, with their axes clustering within 30 degrees of each other, is a fundamentally different statistical situation. If the anomalies were pointing in random directions, you could invoke the look elsewhere effect and dismiss them individually. But they are not random, they converge. And the convergence was not predicted, not searched for, not engineered by anyone. It emerged from independent analyses by independent teams. That pattern, the convergence itself, is arguably the most statistically significant single result in the entire anomaly literature, and it is the one that gets the least attention. There is also a technical debate about the a priori versus a posteriori distinction that I need to address because the conservative camp leans on it heavily. A priori means the test was specified before looking at the data. A posteriori means the test was motivated by the data itself. In general, a posteriori results are weaker because of the look elsewhere effect. You found something weird and then designed a test to confirm it, so of course it looks significant. The anomaly skeptics argue that many of the CMB tests were a posteriori. The cold spot was found by applying wavelets to the data and noticing something unusual. The axis of evil was found by looking at multipole vectors and noticing an alignment. These are valid concerns. But the a priori versus a posteriori distinction is not absolute. Hansen's 2009 extension of the hemispherical asymmetry to high multipoles was explicitly a priori. The prediction was that if the asymmetry is real, it should appear at smaller angular scales. It was tested, it was confirmed. That is predictive science by any standard. Similarly, the Planck confirmation of WMAP anomalies is effectively a priori, in the sense that Planck is an independent instrument, and reproducing a result with independent data is the gold standard of science, regardless of how the result was originally found. Nobody argues that the second detection of gravitational waves was less significant, because the first one told us where to look. Schwartz, COBE, Houghton, and Starkman made this argument explicitly in their 2015 review paper, CMB Anomalies after Planck. They showed that some pairs of the anomalies are demonstrably statistically uncorrelated, meaning they are measuring genuinely different properties of the CMB. When uncorrelated anomalies all point the same way, the combined probability drops rapidly. Their conclusion was that the evidence indicates a significant detection of CMB features at angular scales larger than a few degrees on top of the standard model. That is 4 senior cosmologists publishing in a peer-reviewed journal after 2 decades of data, saying in the most careful language available to them that this is real. Something is there. The standard model does not account for it. The anomalies are not artifacts. They are not noise in any conventional sense. They are features in the data that the concordance model of cosmology does not predict and cannot explain. And the fact that some of them are demonstrably uncorrelated with each other, that they are measuring genuinely different statistical properties of the CMB, means that their combined significance is greater than any individual p-value suggests. You cannot explain the convergence by explaining any single anomaly. The whole is more significant than the sum of its parts. I want you to hold that conclusion in your mind as we move forward, because it is the conclusion that the broader cosmological community has been quietly declining to engage with for over a decade. And now I need to tell you about the moment when the most sensitive CMB instrument ever built confirmed every single one of these anomalies. And the cosmological establishment responded by burying the confirmation in a companion paper. On May 14, 2009, the European Space Agency launched the Planck satellite from Kourou, French Guiana. Planck was the 3rd-generation CMB mission after COBE and WMAP, and it was the best instrument humanity has ever pointed at the oldest light in the universe. 9 frequency channels spanning 30 to 857 gigahertz, angular resolution of 5 arc minutes at its sharpest, temperature sensitivity of about 2 microkelvin per pixel, 50 million pixels. Planck orbited the second Lagrange point, L2, 1.5 million kilometers from Earth, in the direction away from the Sun, and scanned the full sky for 4 years before its helium cryogen was exhausted and the mission ended in 2013. The results were published in waves, the 2013 papers, the 2015 papers, and the final, Legacy 2018 papers. Each wave told the same story. The power spectrum, the mathematical fingerprint of the CMB fluctuations, matched lambda CDM with eerie precision. Planck measured the age of the universe at 13.799 billion years. It measured the Hubble constant at 67.4 kilometers per second per megaparsec. It nailed down the 6 parameters of the standard model with uncertainties of less than 1% in several cases. The headline story was triumphant. Cosmology is solved. But Planck also tested the anomalies, and the results were published not in the flagship papers, but in companions. Paper 23 in the 2013 release, Paper 7 in the 2018 release, both titled Isotropy and Statistics of the CMB. I have read both of them multiple times. The language is remarkable for what it does and what it refuses to do. Planck 2018 Paper 7, authored by Akrami and over 200 co-authors, published in Astronomy and Astrophysics Volume 641. Article A7 states explicitly, the temperature data confirm the presence of several so-called anomalies on large angular scales. Confirmed, not suggest, not are consistent with. Confirmed. But elsewhere in the same paper, it says the lambda CDM model explains the structure of the CMB in detail. Yet, tantalizing evidence has emerged of the presence of such anomalies, indicating that a modest degree of deviation from statistical isotropy persists. Read that language carefully. Tantalizing evidence, a modest degree of deviation, persists. These are words chosen by a committee of over 200 scientists, wordsmithed through months of internal review, calibrated to acknowledge the finding without triggering the institutional consequences of declaring the finding significant. In cosmology, tantalizing evidence is diplomatic language for "we found something we cannot explain, and we are not going to say that directly," because it would undermine the press release about how perfectly everything matches the standard model. And the polarization data, which should have been the tiebreaker, was inconclusive. The paper says that no unambiguous detections of cosmological non-Gaussianity or of anomalies corresponding to those seen in temperature are claimed in the polarization data. Not because the anomalies were absent, not because the polarization was measured and found to be clean, but because Planck's polarization measurements at the largest angular scales, the L equals 2 through about 30 range where the anomalies live, were contaminated by residual systematic effects that the mission was never designed to control at that level of precision. The high-frequency instrument ran out of cryogen in January 2012, and the low-frequency instrument, which continued operating until October 2003, could not achieve the systematic control needed at the lowest multipoles. The satellite was built to be the ultimate temperature mapper, and at that, it was magnificent, but it was not designed to settle the question that its own temperature data had raised. The tiebreaker was a draw, and the draw left the anomalies exactly where they had been since 2003, confirmed in temperature, unknown in polarization, acknowledged but unresolved. This is not a conspiracy. I want to say that explicitly, and I want to mean it. Nobody is hiding data. The papers are public. Anyone in the world can download the Planck maps from the ESA archive and run these analyses themselves. What is happening is more subtle and in some ways more corrosive. It is institutional inertia operating at the scale of an entire field. Let me give you a concrete example of how this works. When the Planck 2018 results were published, the collaboration released 12 papers simultaneously. Paper 1, on the cosmological parameters, the flagship, ran to 66 pages and was the subject of press releases, news coverage, and conference plenary talks around the world. It described the spectacular success of lambda CDM. Paper 7, on isotropy and statistics, the one that confirmed the anomalies, ran to 59 pages and received almost no press coverage. Both papers were written by the same collaboration. Both were based on the same data from the same satellite. But paper 1 told a story the field wanted to hear, and paper 7 told a story the field wanted to ignore. Look at the citation counts. As of 2025, the flagship parameter paper has been cited over 12,000 times. The isotropy paper, the one that confirmed the existence of anomalies that may challenge the foundational assumption of the entire field, has been cited fewer than 800 times. The data is the same. The quality is the same. The difference is in which questions the community considers worth asking. Lambda CDM works brilliantly at small, angular scales. That success generates an enormous institutional investment, not just financial, but psychological, not just in the model, but in the narrative of triumph. Cosmology solved the universe. We know what it is made of. We know how old it is. We know its fate. That narrative is too valuable, too central to the field's identity and its funding justifications to be threatened by ambiguous anomalies at the largest scales that might turn out to be noise. The asymmetry in burden of proof is staggering. If you claim lambda CDM is correct, you need only point at the power spectrum. If you claim something is wrong, you need to explain what and how and why, and rule out every conceivable systematic and demonstrate significance at 5 sigma and survive a decade of gentle dismissal. And here is what makes the current moment particularly troubling. The CMB anomalies are not the only cracks in the lambda CDM framework. The Hubble tension I mentioned earlier, the disagreement between the locally measured expansion rate of the universe and the CMB-derived value, has been growing more significant for over a decade. The SH0E collaboration, led by Adam Rees at Johns Hopkins, measures the Hubble constant using Cepheid variable stars and Type 1a supernovae, and consistently finds a value around 73. Planck, using the CMB and assuming lambda CDM, finds 67.4. The discrepancy is now above 5 sigma by some measures. 5 sigma, the gold standard for discovery in particle physics. And yet, there is no consensus on what it means. Some argue it is a systematic error in the local measurements. Some argue it is new physics. Some argue it is evidence that the cosmological principle itself is flawed, that the universe expands at different rates in different directions, and that the discrepancy between local and global measurements is exactly what you would expect if the assumptions underlying one or both of them are wrong. The CMB anomalies and the Hubble tension are not the same problem, but they point in the same conceptual direction. They both suggest that something about the large-scale structure of the universe does not match what lambda CDM predicts. They both sit in the uncomfortable gray zone between definitely a problem and probably noise, and the field's response to both has followed the same pattern. Acknowledge the data, publish the papers, decline to investigate with the urgency the data warrants, continue teaching the standard model as though it were settled. And that should make you angry, not at any individual scientist, at the system, at the way comfortable answers are amplified and uncomfortable questions are starved of resources. I need to walk you through the explanations that have been proposed for the anomalies, because each one fails in a way that makes the mystery worse, and understanding why they fail is essential to understanding what we are actually facing. The first and most obvious explanation is foreground contamination. This is the one that every reasonable person thinks of first, and it is the one that has been most thoroughly demolished. How a galaxy emits microwave radiation. Dust grains in the interstellar medium absorb ultraviolet light from stars and re-emit it as infrared and microwave radiation. Free electrons spiraling in galactic magnetic fields produce synchrotron radiation. Hot gas in the galactic plane produces free emission. All of these foregrounds contaminate the CMB signal and must be subtracted before cosmological analysis. If the subtraction is imperfect, residual contamination could create spurious features in the maps. This was checked exhaustively. Vielva's original 2004 cold spot paper reported that the non-Gaussianity appeared at every frequency, from 23 to 94 GHz, with no frequency dependence. This is critical. Galactic dust emission is bright at high frequencies and faint at low ones. Synchrotron radiation does the opposite. The CMB, because it is a perfect black body, has no frequency dependence in its anisotropy. If the anomalies appeared only at certain frequencies, or if their amplitude changed with frequency, that would be a smoking gun for foreground contamination. They do not change. They appear with the same amplitude at every frequency. Planck tested this with 9 frequency channels and 4 independent foreground removal algorithms: Commander, NILC, SEVM, and SMICA. Each algorithm uses a different mathematical approach to separate the CMB from galactic and extragalactic foregrounds. Planck 2013 paper 23 stated explicitly that the anomalies are robust against component separation algorithm, mask, and frequency dependence. 4 methods: multiple masks, multiple frequencies. The anomalies survive all of them. This is as close to a definitive ruling out of foreground contamination as you can get in observational cosmology. The second explanation is the look elsewhere effect, and this is the one that deserves the most careful treatment because it is the strongest argument the conservative camp has. The look elsewhere effect is real. It is a genuine statistical concern. If you run 100 statistical tests on a dataset, you expect about 5 of them to come out at 2 sigma just by chance. If you then pick the 5 weird results and declare them anomalies, you are fooling yourself. You looked at 100 things and found 5 that were unusual. That is not unusual at all. The question is whether the CMB anomalies are victims of this effect. And the answer is that it is partially a victim, but not entirely. And the part that is not covered by look elsewhere is the part that should worry you. Each individual anomaly, the axis of evil, the cold spot, the hemispherical asymmetry, the lack of large-angle correlations, was found by examining a specific statistical property of the CMB. The people who found them were looking for deviations from Gaussianity or isotropy. They were, in a sense, fishing. And when you fish, you sometimes catch boots. That is the look elsewhere argument, and for any single anomaly in isolation, it has force. But there are 2 counter-arguments that the look elsewhere camp has never adequately addressed. First is Hansen's 2009 result. The hemispherical asymmetry was originally found at low multipoles, L equals 2 to 40, in the first year of WMAP data. That was a posteriori. You look at the data, you find something weird. But Hansen extended the measurement to L equals 2 to 600, covering much smaller angular scales that had not been examined in the original analysis. This was a genuine prediction. If the asymmetry is physical, it should extend to small scales. If it is a fluke of the low multipoles, it should not. Hansen tested this, and it extended. The asymmetry was present across a wide range of multipoles, with the preferred direction remaining stable. That is not a posteriori. That is a priori. You made a prediction, and it was confirmed. Second, and more important, is the alignment. The individual anomalies were found by different methods, different teams, in different years. Nobody predicted that the cold spot would align with the axis of evil. Nobody predicted that the hemispherical asymmetry would share a direction with the parity preference. The convergence of axes was not something anyone was looking for. It emerged from the data after the individual anomalies had been independently identified, and the convergence is what breaks the look elsewhere argument. You can wave away one weird statistic. You can even wave away 4 weird statistics if they point in random directions. But 4 weird statistics all pointing the same way, with their axes clustering within a few tens of degrees of each other, is a pattern, and patterns are harder to dismiss. Schwartz, COBE, Hutera, and Starkman made this argument explicitly in their 2015 review. They showed that some pairs of anomalies are demonstrably uncorrelated, measuring genuinely different properties of the sky. When uncorrelated anomalies align, the joint probability drops much faster than you would expect from the individual p-values alone. The third explanation is anisotropic cosmology. In the early days of general relativity, mathematicians classified a family of homogeneous but anisotropic solutions to Einstein's field equations, called Bianchi models after the Italian mathematician Luigi Bianchi. These models allow the universe to expand at different rates in different directions. In 2005, Andrew Jaffe and a team including Hume Feldman, Anthony Banday, Hans Christian Eriksen, Krzysztof Gorski, and Frode Hansen showed that a specific Bianchi model, type 7 sub H, could reproduce many of the observed anomalies simultaneously. The model describes a universe with a slight vorticity, a rotation, and a slight anisotropy in its expansion. When you project the resulting CMB pattern onto the sky, it matches the quadrupole-octopole alignment, accounts for parts of the hemispherical asymmetry, and even produces a feature resembling the cold spot. This sounds promising. A single physical mechanism that explains multiple anomalies at once. But the numbers kill it. The best fit, Bianchi type 7 sub H parameters, require a universe with no dark energy and significant vorticity, meaning the universe is spinning. We know the universe has dark energy. Every supernova distance measurement, every baryon acoustic oscillation survey, every CMB power spectrum fit says there is dark energy. Planck constrained the ratio of vorticity to the Hubble constant to less than 8 times 10 to the minus 10 at 95% confidence. When you force the Bianchi model to be physically consistent with the rest of cosmology, the model loses its explanatory power. The anomalies can be fit by an anisotropic universe, but only a universe that contradicts every other observation we have. That is not an explanation. It is moving the problem somewhere worse. The fourth explanation is cosmic topology, and this one is the most elegant and the most tantalizing of the survivors. The idea is that the universe might be finite, but unbounded, like the surface of a sphere, but in 3 dimensions. If you walk far enough on the surface of a sphere, you return to where you started. If you fly far enough through a multiply-connected universe, the same thing happens. And if the fundamental domain of this topology, the size of the basic repeating cell, is comparable to the radius of the observable universe, you would expect to see specific signatures in the CMB. The most famous proposal was the Poincaré dodecahedral space, published by Jean-Pierre Luminet and 4 colleagues in Nature, volume 425, in 2003. The Poincaré dodecahedral space is a positively curved 3-manifold with the symmetry of a regular dodecahedron. Each pentagonal face is identified with the opposite face, but with a rotation of 36 degrees. The result is a finite space that tiles 3-dimensional hypersphere in exactly 120 copies. If the universe has this shape, the maximum wavelength of fluctuations is set by the size of the fundamental domain. Fluctuations larger than the room cannot exist, and that would naturally suppress the quadrupole and the large-angle correlations, exactly as observed. Luminet's paper was followed by an intense search for the predicted matching circles, temperature patterns on pairs of circles that should be identical because they represent the same physical location seen through different paths through the topology. Cornish, Spergel, Starkman, and Komatsu searched WMAP data in 2004, published in Physical Review Letters, volume 92, and found no matched circles above 25 degrees in radius. Planck tightened the constraint in their 2013 paper 26 on background geometry and topology, ruling out compact topologies with fundamental domains smaller than 94% of the radius to the last scattering surface at 99% confidence. But here is the crucial detail that most popular accounts miss. Planck did not rule out topology. It ruled out small topologies, a universe that barely wraps with a fundamental domain comparable to or slightly larger than the observable universe would not produce detectable matched circles because the circles would be too small or too close to the masked galactic plane to identify. And such a topology could still suppress large-angle correlations and produce alignments. The topological explanation is not dead. It is hiding in the gap between what Planck can measure and what actually exists. And the instrument that could have probed deeper into that gap, CMB S4, is gone. The fifth explanation is Mersini-Houghton's multiverse collision. I have already described her predictions. The key point is that the multiverse hypothesis is not just a cold spot explanation. It is a framework that attempts to account for multiple anomalies simultaneously: the cold spot, the giant void, the suppression of low power, the existence of preferred directions. If our universe nucleated from a landscape of vacuum states and interacted with neighboring universes at birth, those interactions would leave precisely the kind of large-scale, directional signatures we observe. The predictions were made in 2006 through 2008. Several align with subsequent observations. The scientific community's objection is that the predictions can be seen as retroactive, fitted to data that was already partially known. That objection has merit, but it does not settle the question. And the question itself, whether the CMB anomalies could be evidence of a multiverse, is one of the most consequential questions in all of physics. If the answer is yes, it means our universe is not all there is. It means there is something outside, something that pressed against us and left a mark. It means the boundary conditions of our cosmos were set not by some abstract initial condition, but by a physical interaction with another reality. And nobody has the data to confirm or rule out that possibility. The experiment that would have provided it was cancelled 7 months ago. I am not going to tell you which explanation is correct, because nobody knows. That is the honest answer, and the audience deserves honest answers. But I am going to tell you what every serious analysis agrees on, regardless of which explanation they favor. Something is there. The anomalies are real. They are not instrumental artifacts. They are not foreground contamination. They are not confined to one satellite or one analysis method. They span the largest angular scales of the cosmic microwave background. They persist across 3 decades of increasingly precise observations, and they align with each other in a way that standard cosmology does not predict and cannot explain. If the hemispherical power asymmetry is physical, the cosmological principle is broken. The universe is not statistically isotropic. It has a preferred direction, a gradient, an orientation, and everything downstream of the cosmological principle. Every distance measurement, every dark energy calculation, every estimate of the age of the universe is built on a foundation that contains a crack. Think about what that means concretely. The measurement of dark energy, the discovery that the expansion of the universe is accelerating, won the 2011 Nobel Prize. It is based on measuring the distances to Type 1a supernovae, comparing those distances to their redshifts, and fitting the result to a model that assumes the universe expands the same way in every direction. If the expansion is anisotropic, if there is a 7% difference in fluctuation power between hemispheres that traces back to a genuine asymmetry in the universe's structure, then the supernova distances may be systematically biased in a direction-dependent way. The Hubble constant, which is the expansion rate of the universe, and which has been the subject of a bitter decade-long disagreement between different measurement methods, could itself be direction-dependent. The so-called Hubble tension, the disagreement between the locally measured value of about 73 kilometers per second per megaparsec and the Planck-derived value of 67.4, might not be a tension at all. It might be a direction. Different groups measuring in different parts of the sky and getting different answers, because the universe is actually different in different directions. A 2013 paper by Mariano and Perivolaropoulos examined the directional dependence of the dark energy equation of state using supernova data and found hints of anisotropy roughly aligned with the CMB dipole direction at about 2 sigma. Not definitive, but the same direction again. Always the same direction. If the axis of evil is real, The universe's largest patterns share an alignment that the standard model does not predict. The quadrupole and octupole know about each other. They are correlated across angular scales that should be independent. Something connected them at the moment of creation, or something is connecting them now, and neither option is comfortable. If the cold spot is primordial, something punched a hole in the cosmic microwave background 13.8 billion years ago that is not accounted for by any known physics. The supervoid explains a fraction. Standard statistics say it should not be there. Mersini-Houghton says it is the bruise left by another universe pressing against our own. Others say we need a different model of inflation, or a different topology, or an entirely different framework. Nobody has an answer that works. And here is the worst part. I have been saying this. All of these anomalies, every axis, every preferred direction, clusters near the ecliptic plane, near the plane of our solar system, aligned, roughly, with the direction of our motion through the cosmic microwave background. And there are only 3 ways to interpret that. Option 1. It is a coincidence. The anomalies have preferred directions because the universe genuinely has preferred directions, but the alignment with the ecliptic is accidental. The probability of that alignment happening by chance is small, somewhere between 1 in 100 and 1 in 1,000, depending on how you calculate it. But small probabilities happen. We live in a specific place. That place happens to be near a direction that happens to be near the anomaly axes. Coincidences occur. This is the safe answer. It is probably the correct answer. And yet the word probably is doing an enormous amount of work in that sentence, and nobody can tell you exactly how much. Option 2. There is an unknown systematic effect associated with our solar system or our local environment that has contaminated 3 independent satellite missions spanning 30 years of observations. COBE launched in 1989. WMAP launched in 2001. Planck launched in 2009. They used different orbits, different detectors, different frequency ranges, different data analysis pipelines, different foreground removal methods. If a systematic effect fooled all 3, it would have to be something that produces a signal at all microwave frequencies with no frequency dependence. That mimics the statistical properties of a primordial cosmological signal. That appears only at the largest angular scales, and that has a specific angular structure aligned with the ecliptic. No such systematic has ever been identified. That does not mean it cannot exist. But it requires a systematic that is more exotic and more finely tuned than any systematic ever encountered in observational astronomy. At some point, the hypothetical systematic needed to explain away the anomalies becomes more exotic than the anomalies themselves. Option 3. The universe genuinely has features that are related to our position within it. I need to explain why this option makes physicists so uncomfortable. Because the discomfort is not aesthetic. It is historical. It is philosophical. It is in a very real sense existential. For 500 years, science has been moving humanity away from the center. Copernicus moved the Earth away from the center of the solar system. Kepler showed the orbits were not even circular, destroying the geometric perfection that had placed us at the center for 2 millennia. Galileo saw the moons of Jupiter and the phases of Venus and demonstrated that not everything orbits us. Newton showed that the same laws govern the heavens and the earth, making our planet ordinary. Hubble showed that our galaxy is one of many. The cosmological principle, the assumption that the universe looks the same from every location and in every direction, is the ultimate expression of this 5-century trajectory. We are not special. Our location is not special. Our direction is not special. There is no center. And now the oldest light in the universe seems to be pointing at us. Its Anomalies cluster near the plane of our solar system. Its axis of evil aligns with the direction we are moving through the CMB. Its asymmetries correspond to the geometry of our local cosmic neighborhood. This does not mean we are at the center. There are models, topology, anisotropic inflation, primordial fields that could produce alignments without privileging any location. But none of those models have been confirmed, and the alignment sits there, unexplained, empirical, reproduced by 3 satellites, waiting for someone to either explain it or accept its implications. The history of science suggests that when data consistently points in a direction that existing theory cannot accommodate, the data is usually right and the theory is usually wrong. Not always, but usually. And when it is wrong, the resolution is not a patch, not an epicycle, not an adjustment. It is a revolution. Copernicus did not fix Ptolemy. He replaced him. Einstein did not fix Newton. He subsumed him. Whatever explains the CMB anomalies, if they are real, will not be a minor modification to lambda CDM. It will be something that changes the framework. There are theoretical models that could produce option 3 without making us the center. A universe with non-trivial topology, a Poincaré dodecahedral space, or a more complex multiply-connected manifold could create correlations at specific locations without any location being privileged. Anisotropic inflation could imprint a preferred direction without breaking homogeneity. Primordial magnetic fields could thread through the cosmos and leave an imprint on the CMB that appears aligned from our vantage point. None of these models have been confirmed. Several have been partially ruled out. Planck constrained the Bianchi models, those anisotropic cosmologies that allow the universe to rotate and expand asymmetrically. The best fit Bianchi parameters require a universe with no dark energy and significant vorticity, which contradicts everything else we know. Planck ruled out compact topologies with a fundamental domain smaller than 94% of the distance to the last scattering surface. What remains is a narrow window of allowed models that are just barely consistent with the data and just barely capable of explaining the anomalies. The cosmic topology explanation deserves more attention than it gets because it is the most elegant of the surviving possibilities. Jean-Pierre Luminet and 4 colleagues published a paper in Nature, volume 425, in 2003, proposing that the universe has the shape of a Poincaré dodecahedral space. Imagine a dodecahedron, a 12-sided solid made of pentagons. Now imagine that each face of the dodecahedron is identified with the opposite face, so that if you walk out through one pentagonal face, you re-enter through the opposite one. The space is finite, but has no boundary. It wraps around on itself. And if the size of this fundamental domain is comparable to the distance light has traveled since the Big Bang, then you would expect to see specific signatures in the CMB. The lack of large angle correlations would be explained naturally, because the universe is not big enough to support fluctuations on those scales. There is a maximum wavelength set by the size of the room. Luminet's model specifically predicted a suppressed quadrupole, which matched the data, but it also predicted matching circles in the CMB, pairs of circles on the sky showing identical temperature patterns. Cornish, Spergel, Starkman, and Komatsu searched for these circles in 2004 using WMAP data and found none above 25 degrees in radius. Planck tightened the constraint. Small topologies with fundamental domains much smaller than the observable universe are ruled out. But a topology where the fundamental domain is close to the size of the observable universe where the universe barely wraps, is still allowed. It is not testable with current data. It will require better polarization measurements at the largest scales. Which brings me to the moment this story becomes genuinely tragic. In the early 2010s, the CMB community began planning the next great experiment, CMB S4, Cosmic Microwave Background Stage 4. The name itself tells you the lineage. Stage 1 was COBE, Stage 2 was WMAP and the first generation of ground-based experiments. Stage 3 was Planck and its contemporary ground-based successors like the Atacama Cosmology Telescope and the South Pole Telescope. Each generation improved on the last by roughly an order of magnitude in sensitivity. Stage 4 was supposed to be the end of the line, the experiment so sensitive that it would exhaust the information content of the CMB at all, but the very largest angular scales. The specifications were staggering. Over 500,000 superconducting transition edge sensor bolometers, cooled to a fraction of a degree above absolute zero, distributed across 2 sites, a large aperture telescope at the geographic South Pole, where the atmosphere is driest and most stable on Earth, and a set of smaller telescopes on Cerro Toco in Chile's Atacama Desert, at an altitude of 5,200 meters. The detectors would measure the polarization of the CMB in multiple frequency bands simultaneously, building up a map over years of observation that would reach a noise level roughly 10 times lower than Planck at the same angular scales. The total project cost was estimated at roughly $900 million, split between the Department of Energy and the National Science Foundation. Among many other scientific goals, CMB S4 was designed to search for the faint B-mode polarization signal from primordial gravitational waves, which would be direct evidence of cosmic inflation. It would have constrained the sum of neutrino masses with a precision unreachable by any other technique. It would have mapped the distribution of dark matter through gravitational lensing of the CMB. And critically, for the story I am telling you, it would have measured E-mode polarization at the largest angular scales with enough precision to definitively determine whether the temperature anomalies are physical. The logic is straightforward. The CMB is polarized. When photons scatter off electrons at the surface of last scattering, the polarization carries information about the local quadrupole of the radiation field at each scattering event. If the anomalies in the temperature map are genuinely imprinted at the surface of last scattering by a real physical mechanism, whether it is anisotropic expansion, non-trivial topology, a multiverse collision, or something else, that mechanism should also affect the polarization. The E-mode polarization pattern should show the same anomalies as the temperature pattern, not identical, but correlated. If the anomalies appeared in polarization, the debate would be over. They would be confirmed as cosmological. If they did not appear, the anomalies would be identified as some form of systematic effect, or the most elaborate statistical coincidence in the history of science. Either way, the question would have been settled. The project had been in development for over a decade. Hundreds of scientists at dozens of institutions had structured their careers around it. Graduate students had written dissertations on the detector technology. Postdocs had spent years on site surveys and optics design. Engineers had developed new fabrication techniques for the superconducting arrays. The project had passed multiple successful reviews by both DOE and NSF. It had been endorsed by the Astro 2020 Decadal Survey, the once every 10 years report by the National Academies of Sciences that sets the priorities for the entire US astronomy and astrophysics community. It was, by every formal measure, the highest priority project in its category. On July 9th, 2025, the Department of Energy and the National Science Foundation jointly announced they would no longer fund CMB S4. The project was dead. Regina Ramiecka, the DOE's Associate Director for High Energy Physics, told Science magazine on the day of the announcement, it had become obvious that the goals of the CMB S4 project would be difficult to achieve in a timely, cost-efficient way. This was not a purely monetary decision. The South Pole infrastructure was aging. The logistics of operating telescopes at one of the most remote and hostile locations on Earth were becoming untenable. The post-pandemic budget reality left no room for a $900 million experiment when other priorities demanded funding. John Karlstrom, a physicist at the University of Chicago who had been one of CMB S4's co-leaders, was quoted in Scientific American in a July 23, 2025 article by Nadia Drake. His words carry the weight of someone who watched a decade and a half of work dissolve. You know, when I started this in 2013, I thought, this is going to be great. We will get on the air in 2020 and I can retire in 2025. Instead, the expectation was that even with the surviving experiments, they could get telescopes on the air as early as 2032, with combined results in 2040, 2041. Think about that timeline. The anomalies were first detected in 2003. CMB S4 would have settled the question in the late 2030s. With its cancellation, the next chance comes from two surviving paths, and neither is guaranteed. The Simons Observatory, funded primarily by the Simons Foundation with additional support from public agencies, is now operating on Cerro Toco in Chile's Atacama Desert at an altitude of 5,200 meters, where the air is thin and dry and the microwave sky is as transparent as any ground-based site on Earth. Its large aperture telescope, 6 meters in diameter, saw first light in March of 2025. Its 3 small aperture telescopes, each half a meter, have been taking data since 2023. The observatory will deploy over 60,000 detectors across 6 frequency bands and will improve on Planck's sensitivity at intermediate angular scales by a significant factor. But the Simons Observatory was designed primarily as a B-mode polarization experiment, optimized for detecting the signature of primordial gravitational waves. It was not designed to be the definitive test of the anomalies at the very largest angular scales. Ground-based telescopes, no matter how sensitive, have a fundamental limitation. They cannot observe the largest angular scales of the CMB as cleanly as a satellite, because the atmosphere emits microwave radiation that contaminates the signal, and the contamination is worst at the largest scales. The Simons Observatory will contribute to the anomaly question. It will improve constraints, but it will not settle it. It is a Stage 3 experiment. CMB S4 was Stage 4 for a reason. The other path is Lightbird, and it is the one that matters most for the story I am telling you. Lightbird is a Japanese satellite mission led by JAXA, the Japan Aerospace Exploration Agency. It was designed specifically to measure CMB polarization across the entire sky from space, above the atmosphere, without the thermal contamination that cripples ground-based measurements at the larger scales. The satellite would carry 3 telescopes covering 15 frequency bands from 34 to 448 gigahertz, providing the frequency coverage needed to separate the CMB from galactic foregrounds. Its primary science goal is to detect or rule out primordial gravitational waves at an exquisitely sensitive level, a tensor to scalar ratio of 0.001. But the same data, the same full sky polarization maps at the larger scales would provide near-cosmic variance limited measurements of E-mode polarization, the exact data needed to settle the anomaly question once and for all. If light bird flies and the temperature anomalies are mirrored in E-mode polarization, the debate is over. The anomalies are cosmological. The cosmological principle is challenged. New physics is required. If light bird flies and the polarization is clean, the anomalies are identified as some form of unexplained systematic or the most elaborate coincidence in observational cosmology. Either way, we would have an answer. But Lightbird is in trouble. It was originally targeting a launch at the end of Japanese fiscal year 2032, which would have been early 2033 on the calendar. But in October of 2024, KAK, the Japanese High Energy Accelerator Research Organization, which was contributing key cryogenic technology and detector components to the project, withdrew from the collaboration. The reasons are not entirely public, but the impact was immediate. The JAXA mission page, updated September 25, 2025, now says the team is reviewing the plan, aiming for a launch in JFY 2036. And anyone who has worked in space science knows that launch dates slip. 2036 could become 2038, could become 2040, could, if the political winds shift or the budget landscape changes, become never. 2036, the anomalies were found in 2003. The satellite that might settle the question will not fly for another decade, at the earliest, and possibly much longer. That is a third of a century of the most fundamental open question in observational cosmology sitting unresolved. A third of a century in which the data has been confirmed by every instrument that has looked at it, in which the statistical arguments have been refined and strengthened by 20 years of analysis, in which the axes have stubbornly refused to move, not because the question is unanswerable, not because the physics is intractable, not because the technology does not exist, but because the institutions that fund science could not sustain the political will and the financial commitment required to answer it. And this is where I come back to the people, because the people are what transform this from a technical dispute into something that matters on a human scale. Kate Land discovered the axis of evil as a PhD student at Imperial College London in 2005. She was 20-something years old at the beginning of what should have been a long career in cosmology, and she co-authored a paper that identified one of the most provocative features in the most important dataset in observational cosmology. She left the field 4 years later because the career structure of academic physics made it impossible for her to build a stable life while doing the work. The postdoc circuit, the constant moving, but temporary contracts, the uncertainty, the silent understanding that you are disposable until you are tenured, and that tenure comes, if it comes at all, after a decade of transience. She chose stability. She chose London. She chose finance. And the anomaly she named is still there, 20 years later, confirmed by Planck, unexplained by any model, pointing in a direction that nobody can account for. The axis does not know that the woman who named it left. Joao Magueijo named the axis with the deliberate provocation of a man who had already been burned by the establishment for his varying speed of light theory and had nothing left to lose professionally. He chose the name Axis of Evil, knowing it would be impossible to ignore, knowing it would force citations, knowing it would make every subsequent paper on the quadrupole-octupole alignment carry his fingerprint. It was a brilliant act of scientific branding. The name forced the community to engage, at least superficially. But engagement is not the same as action. And the community's response over 2 decades has been to acknowledge the finding in companion papers, cite it in literature reviews, and then redirect attention to the standard model's successes. Magueijo is still at Imperial College. He is still publishing. He is still, by all accounts, the same combustible, brilliant, inconvenient presence he has always been. And the establishment is still finding ways to absorb his work without being changed by it. Laura Mersini-Houghton, born under a communist dictatorship that sealed its borders and controlled its citizens' thoughts, became a physicist who asks whether the borders of reality itself might be more permeable than we assumed. Her prediction of the cold spot from multiverse theory remains neither confirmed nor refuted. The instrument that could have distinguished her hypothesis from the alternatives was just cancelled. Patricio Vielva found the cold spot as a newly minted PhD using a technique his own group had developed, and the field spent 2 decades trying to explain it away with a supervoid that accounts for less than 20% of the signal. And COBE, Hutera, Schwartz, and Starkman have been publishing the same conclusion in increasingly refined form, year after year after year, still lacks a convincing explanation. They've been saying this for over 20 years. The field hears them, the field nods, and the field does not act. I am going to follow the implication now to the place where it touches you, because that is what this evidence demands. You exist in a universe, not abstractly, physically. The atoms in your body were forged in stars that burned and died billions of years before you were born. The hydrogen in every water molecule in your blood was created in the Big Bang, in the same hot, dense plasma that emitted the cosmic microwave background 380,000 years after the Big Bang. That plasma cooled below 3000 Kelvin. The electrons combine with protons to form neutral hydrogen, and the photons were released. Those photons have been traveling ever since. They are arriving at your planet right now, from every direction at 2.725 Kelvin. And if you had a radio telescope in your backyard and pointed it at the sky, you would hear the same static that Penzias and Wilson heard in 1965, the oldest sound in the universe, the afterglow of creation. And that afterglow has a pattern in it that nobody can explain, a pattern that was not predicted by any model, a pattern that was discovered by accident when the instruments got good enough to see it, a pattern that has survived 3 decades of the most precise measurements in the history of science, a pattern that points in a direction, that converges on an axis, that aligns, for reasons nobody can explain, with the plane of the solar system that your planet orbits within. The conservative interpretation is that it is noise, a statistical fluctuation in a finite dataset, an artifact of running too many tests and finding the ones that look weird. That is a defensible position. It is probably correct. History is full of tantalizing signals that evaporated when better data arrived. The canals of Mars, the Pioneer anomaly, cold fusion. 3 sigma results have a way of melting in the light of 5 sigma observations. But the canals of Mars did not appear in 3 independent telescopes. The Pioneer anomaly did not point in the same direction as 4 other unrelated anomalies. Cold fusion could not be reproduced across different labs. The CMB anomalies have been reproduced by COBE, WMAP, and Planck. They have been tested against every known systematic. They point the same way. They refuse to go away. I keep coming back to the axis, the convergence. 4 different anomalies found by 4 different methods by different teams in different years, all pointing within 30 degrees of the same spot in the sky. The look elsewhere effect explains why one anomaly might be a fluke. It does not explain why 4 flukes would conspire to point the same direction. That is the fact that nobody has an answer for. Not the individual anomalies, the convergence. And I keep thinking about what Lawrence Krauss said back in 2006 when the WMAP anomalies were still fresh. The new results are either telling us that all of science is wrong and we are the center of the universe, or maybe the data is simply incorrect. Or maybe it is telling us there is something weird about the microwave background results, and that maybe there is something wrong with our theories on the larger scales. Krauss was being provocative. He was laying out the logical possibilities in their starkest form. But 20 years later, none of those possibilities has been eliminated. The data has been confirmed as correct by Planck. We are almost certainly not at the center of the universe. Which leaves the third option. Something wrong with our theories on the larger scales. And the field has spent 2 decades trying not to look at that option too directly. I spoke earlier about institutional inertia, about the way the field handles uncomfortable results by acknowledging them in companion papers and declining to investigate them with the urgency they deserve. But I want to zoom out further, because there is something deeper happening here that I think matters beyond cosmology. The history of science is not a history of steady, linear progress. It is a history of long periods of stability punctuated by crises. Thomas Kuhn called them paradigm shifts. The Ptolemaic model worked for 15 centuries. The Newtonian model worked for 2. Quantum mechanics has been the foundation of physics for 100 years, and the lambda CDM model has been the foundation of cosmology for about 25. Each of these frameworks was spectacularly successful. Each of them explained the existing data with extraordinary precision, and each of them eventually encountered anomalies that could not be accommodated. The crucial insight from the history of science is this: the anomalies never look important when they first appear. They always look like noise. They always look like flukes. The establishment always has good statistical reasons to dismiss them. The people who take the anomalies seriously are always a minority, and the resolution, when it comes, always comes from outside the framework, not from within it. You cannot fix Ptolemaic astronomy by adding more epicycles. You cannot fix Newtonian gravity by adjusting the gravitational constant. The fix comes from a fundamentally new idea that reframes everything. I am not claiming that the CMB anomalies are the harbinger of a paradigm shift. They might be nothing. They probably are nothing. But the pattern is familiar. The anomalies are there. The field acknowledges them. The field declines to investigate them with the resources they would require, and the few people who dedicate their careers to studying them are treated with polite marginalization. I want to pause on that word, marginalization. It is not dramatic. It is not violent. It is not overt censorship. It is something much quieter. It is not getting invited to the plenary session at the conference. It is having your grant proposal ranked lower because the reviewers think the anomalies are probably noise and the money would be better spent elsewhere. It is having your paper accepted but placed in the companion volume rather than the flagship. It is being described as interesting but provocative in letters of recommendation, which in academic code means probably not worth hiring. It is a slow, gentle, deniable process of being moved to the margins, not because your science is wrong, but because your science is inconvenient. And the cumulative effect of that marginalization is that the anomalies remain in their gray zone, not investigated enough to be resolved, not ignored enough to be forgotten, just sitting there. The most important unresolved problem in observational cosmology, treated as a footnote. Kate Land left the field. Mersini-Houghton was politely sidelined. COBE, Hutterer, Schwartz and Starkman keep publishing. Magueijo keeps provoking. And the rest of the field keeps publishing papers about how perfectly lambda CDM fits the power spectrum, which it does at small angular scales, where the anomalies do not live. I want to be fair to the conservative camp because fairness matters. They are not being dishonest. They have legitimate statistical concerns. The look elsewhere effect is real. The a posteriori nature of many anomaly tests is real. The cosmic variance limitation at low multipoles is real. And it means that some of these anomalies may genuinely be unprovable with any conceivable dataset, which is not a comfortable situation for a field that wants definitive answers. There is a reasonable, intellectually honest position that says, we see suggestive features, we cannot determine their significance with current data, and we should wait for better data before drawing conclusions. That is a defensible position. But here is the thing about that position. It has been the position for 22 years. And in those 22 years, the field has systematically defunded, delayed, and cancelled every instrument that would have provided the better data that the conservative camp says is needed before they will take the anomalies seriously. You cannot say, we need better data, and then cancel the experiments that would provide it. That is not scientific caution. That is a circular argument dressed in the language of rigor. The data is sitting there. It has been sitting there since 2003. 22 years, 3 satellite missions, 50 million pixels, 1 part in 100,000 precision. The anomalies have been confirmed, reconfirmed, tested against every known systematic, and published in the most rigorous journals in the field. They survive everything. They go nowhere. They just sit in the data, patient, stubbornly present, waiting for an instrument that can finally determine whether they are the fingerprint of something profound or the cruelest false signal in the history of observational science. And we just took that instrument away. Penzias and Wilson cleaned the pigeon droppings out of the antenna, and the hiss remained. They spent months looking for the error, convinced it was instrumentation, convinced it could not possibly be the universe itself trying to tell them something. The hiss was the cosmic microwave background. The most important signal in the history of cosmology was sitting in their noise floor, and they almost dismissed it because it did not fit what they expected to find. Robert Dicker, 40 miles away at Princeton, had the theory but not the data. Penzias and Wilson had the data but not the theory. Dickey never shared the Nobel. The universe does not care about credit or fairness. It simply emits its light and waits. And now, 3 generations later, we are staring at anomalies in the same light. Anomalies that look like noise to the people who do not want them to be signal. Anomalies that are published in companion papers, discussed in footnotes, acknowledged with hedging language that never quite commits to saying what the data shows. The Planck collaboration used the word confirmed in their 2018 paper on isotropy and statistics. They confirmed the anomalies. And then they published the confirmation in paper number 7 of a series of 12, while paper number 1 on the cosmological parameters made the front pages. George Smoot stood at a podium in 1992 and compared the COBE results to looking at the face of God. It was an exaggeration, a moment of press conference theater, and it caused a rift within the COBE team that took years to heal. But there was something correct in the instinct behind it. The CMB is not just data. It is a portrait of the infant universe. It carries information about the moment the cosmos transitioned from opacity to transparency, from a featureless fog of plasma to the luminous, structured, recognizable universe we inhabit. It is the closest thing to a birth photograph that the universe will ever produce. And the birth photograph has an anomaly, a mark, a set of features that should not be there according to our best understanding, that align with each other in a way our models do not predict, and that point in a direction that our models say should not be special. The universe sat for its portrait, and the portrait came back with something unexpected in the background, something nobody can identify, something that has been staring at us from the oldest light in existence for 22 years and counting. Laura Mersini-Houghton thinks it is the fingerprint of another universe. She may be right, she may be wrong, but she saw something in the data that most of her colleagues were unwilling to consider, and she followed it to its logical conclusion. And the logical conclusion was that our universe has a neighbor, and the neighbor pressed against us at the moment of creation and left a mark on the sky. Kate Land saw the axis. She and Magueijo gave it a name designed to be impossible to ignore, and the field found a way to ignore it anyway. She left cosmology for a more stable life. The axis stayed. COBE, Houghton, Schwartz, and Starkman have been doing the quiet, unglamorous work of documenting the anomalies, year after year, paper after paper, with the meticulous precision of people who know they are right about the data, even if nobody can yet say what the data means. Their most recent conclusion is the same as their first. 2 decades ago, still lacks a convincing explanation. And John Karlstrom, who spent 12 years building CMB S4, the instrument that would have settled the question, watched it die in a budget meeting. You know, when I started this in 2013, I thought, this is going to be great. The oldest light in the universe has a pattern. The pattern has a direction. The direction is real. And the next chance to understand what it means will not arrive until the mid-2030s, when a satellite that has not yet been built reaches an orbit that has not yet been funded around a question that has been unanswered for longer than many of the scientists who study it have been alive. The sky is still glowing at 2.725 Kelvin, as it has been for 13.8 billion years, carrying a message that was stamped into the light at the moment the universe first became transparent, a message that says, there is a direction, there is an axis, there is a pattern in the noise, and it has been here all along. We have not read it yet, and right now we are further from reading it than we were a year ago. That is not because the universe is hiding the answer. The universe put the answer in the oldest light there is and made it visible from every direction. The universe put it everywhere. We are the ones who keep looking away.